Hey guys, today we are going to be solving an interesting problem. This is called as the Prandtl-Meyer shock problem. So here the idea is we actually have a supersonic inflow into a duct and then there is a sharp corner. We are going to develop a lot of Mach waves. These are called as weak Mach waves and there are infinite of them. Okay, and that's actually going to fan out, creating this particular pattern right here. So here in the leading edge, the angle that this shock wave makes is proportional to the inlet Mach number, and then the trailing edge of the shock depends on the outflow Mach number. We are also going to be setting this problem as a two-dimensional problem. Shocks are extremely important in CFD. You can see them in different applications. In today's class, you will learn how to actually set it up. So the setup is quite simple. So I already have the geometry here. You have access to the STL file. So what you are going to be doing is you are going to be flagging this particular case as a two-dimensional geometry. I'm not going to be doing a step-by-step tutorial here because I think we have done enough 2D simulations already. So quick run through. So here I'm still doing a steady state simulation. You can see that I'm running it up to 25,000 cycles. All right, so I have my inlet here, outlet here, and then since it's 2D, the front and back boundaries are going to be two-dimensionals, and then the top and bottom walls are going to be slip boundaries. Okay, so with respect to Solver parameters, I'm not changing anything. Now the fundamental difference is that at the inlet, I'm basically providing a supersonic inlet condition. So the velocity along the x-axis is 680 meters per second. Now at 286 Kelvin, the speed of sound is roughly 340. So the inlet Mach number is 2.0. All right. So that is my inlet condition, and you can see that the inlet species is just air. Now at outlet, you can see that I'm using a Neumann boundary condition. Now as part of your homework assignment, you are going to figure out what Neumann boundary conditions means. If a boundary condition is Neumann, how are values determined at the boundaries? You are going to be researching that and you are going to be letting us know in your solution. The other thing you need to figure out is for supersonic outlets, why is all the boundary conditions set to Neumann boundary conditions? So for this particular problem, you need to make sure that everything in your outlet is Neumann boundary condition. With respect to 2D boundaries, there is no surprises. It's fairly simple. The top and bottom walls are slip boundaries. Okay, so that's basically it. The other thing that you need to pay attention to is the initial conditions. So here I'm initializing the domain with 680 meters per second. As part of your challenge, you are going to be running two problems. In the first problem, you are going to be setting up the initial conditions as 100 meters per second, which is subsonic, and in the second attempt you are going to be setting it up as 680 meters per second, and you are going to tell us how the results are going to change. For turbulence modeling, what I'm doing is I'm selecting RNGK epsilon. Again, we have not talked about turbulence modeling yet, so in this particular case we are using the default value. So the next thing that we need to talk about is the base grid. So the base grid for this problem is 0.8. All right, so I'll enable the bounding box here so that you can see what the dimension of the geometry is. For this particular dimension, my base grid is 0.8 and I'm having the same base grid size in all the three directions. Now the interesting thing that we are doing here is we are enabling adaptive mesh refinement. What is that? So if I go back to this video, you can see that in certain areas the mesh is fixed, whereas the place where the shock occurs, you see that we are using finer cells. This is called as adaptive mesh refinement, and in this particular case I'm using a temperature based adaptive mesh refinement so that I monitor the curvature in temperature. So curvature means second order derivative in temperature. I'm monitoring that whenever the curvature of temperature is greater than a particular value, I refine the mesh. So you can think of this as the subgrid scale temperature. All right, so if I go back to Converge here, and if I open adaptive mesh refinement, you can see that I've enabled temperature AMR in region 0. So what I'm going to do is I'm going to tell you how I set this up. So I went to grid control and I made sure that adaptive mesh refinement is first checked. All right, so once adaptive mesh refinement is checked, I click on AMR, and the first thing I do is I basically set the maximum number of cells that I want. In this case, I'm going to start out with 200,000 cells. So that is the maximum cell count possible. All right. And then I'm saying that AMR is available in only region 0. So by default, you would see something like this. What you need to do is you need to select your region and you need to place it under the active regions. Only then AMR is going to be active. then we are going to be choosing the type of AMR. So in this particular case, you can choose velocity AMR or temperature AMR, because when a shock occurs, both of these quantities are going to change a lot. So what I'm doing is I'm using a temperature AMR, and then the subgrid scale temperature difference is 0.05 Kelvin. So whenever the subgrid scale temperature is greater than 0.05 Kelvin, AMR is going to refine. And the maximum embedding level for AMR is set to 2. So if I open up this video, right, you can see that this right here is your base grid. And if I pause the video somewhere here, you can see that from the base grid size, this is your first level of refinement. That is, if you have embed scale of 1, this is the refinement that you will have. If you have embed scale of 2, everything is going to get refined one more time. Like I said, Converge uses an octary data structure. So the refinement formula is quite simple. So if your refinement level is n, then your grid size is going to be base grid divided by 2 power n. Since our base grid is 0.8 meters and our embed level is 2, the new grid size, or the smallest grid size, is going to be 0.8 divided by 2 power 2, which is 4. 0.8 by 4, which is going to be 0.2 meters. So that is the smallest cell that we will have in our particular simulation. Now, if you increase the embed scale, your cell sizes are going to get even more smaller. And then with respect to subgrid criterion, what I want you to do is I want you to use different values for the subgrid scale criterion to understand what actually happens. Alright, so that's also part of your assignment. So once I OK this, that's basically it. I export my simulation and then I run it. Now at this point, you must be extremely comfortable in running the simulation and post-processing the simulation. So in this particular case, what I'm doing is I'm plotting the temperature. Okay, so you can look at velocity. You can also look at the Mach number to see how it changes. So that's going to be your assignment for this week. Alright, let me know if you have any questions. I'll see you guys in the next video. Bye.